Okay, so yesterday we wrote down the mean value theorem. Here's a picture of what we did yesterday. Again, here's our work, okay? Remember what we were doing? We were just playing around, and I had you guys try to draw a secant line from the first to the last point. Remember that? And then it asked you if you thought there might be any tangent lines that run parallel to that secant line. Right? And we said sometimes yes, sometimes no. But we said the ones that all had a yes, the ones where we were able to do this, they all had something in common. They were all, well, not all, but most of them were continuous on the interval, differentiable on the interval, right? So what we decided to do is just write a theorem where if the function is continuous and differentiable across the interval from A to B, continuous for the whole interval, and at least differentiable between A and B, like exclusive, then we believe there will be one at least. And that's kind of all we could conclude. So what happens is this becomes a theorem with three ideas. One is, well, there's two ideas. The first idea is simply, does this function qualify for the mean value theorem? Okay, some do, some don't. And if the function qualifies for the mean value theorem, meaning it's continuous and differentiable, then where is that green line? That would be like part two of the question. And then at that point, it becomes more of a formula. At the end of this theorem is a formula, say. So you bust out and start using the formula to get C. That's what happens. Okay, so let's just do a couple examples. The theorem is super important, so let me at least copy and paste it to the other side, to the next page.
How does that bottom left one fit into the
Okay, let's go back and look at that one. So you're saying in this diagram here, why is it that we're saying that this has a tangent line that's parallel to the red?
I'm just saying because the equation says it says continuous and differentiable.
Yeah, the hypothesis of this, there's two hypotheses for this theorem. First of all, the function has to be continuous and differentiable, and then we're guaranteed at least one. It doesn't say anything about functions that are not continuous and differentiable. So although this function is broken, we found one. This theorem is only good for unbroken, non-sharp turn, no vertical tangent type beautiful functions like this one, or this one. And basically it guarantees us one of those lines. There are other graphs that defy the hypotheses but affirm the consequence. Like this one has a tangent line, but it's not because it was continuous and differentiable. It just happens to happen. It's parallel to the secant line. You have to be very careful in logic to never deny the antecedent or affirm the consequent. That means this: never treat cause as effect, and never treat effect as cause in logic. Right? If I told you that I will give you 20 bucks if you wash my car, the condition is you need to wash my car. Okay, and then you'll get 20 bucks. That's the promise. Okay, now if you don't wash my car, I might give you 20 bucks anyway. Right? That theorem doesn't anything about what happens if you don't wash my car. The theorem simply says, if you wash my car, I'll give you 20 bucks. So for a person who doesn't wash my car, we don't know what's going to happen to that person, if they'll get 20 or not. So you cannot assume that the converse of this is true, or the inverse of this is true, this statement is true, and that's it. If it's continuous and differentiable, namely the first graph and the last graph, then we're guaranteed at least one of these lines. And the last one had 3, right? Okay, so the questions are all going to be based on this theorem, right? And so let's see what one might look like. So your instructions might look something like this. If f of x is equal to x to the 2/3, and the interval, let's say, is from -1 to 1, determine if f of x meets the conditions for the mean value theorem
If it does, find C such that f prime of C is equal to f of B minus f of A over B minus A. All right, so the first thing we have to do is confirm that this question is even worth evaluating with the mean value theorem. Okay? This formula is only good if the two conditions are met. Okay, so a quick sketch of this would be really helpful. But let's say that we don't have that luxury. We don't know that this is the seagull graph. Okay, because that's what this is. It's the seagull graph. But let's just say you didn't know that. You'd ask, okay, well, first I'm going to ask if it's continuous. Is f continuous on negative 1 to 1? What do you think? Well, that's like asking if it has any asymptotes along the way, or if it has any jumps or holes along the way. Well, what is the domain of this function? All real numbers. You can square any number and then take the cube root. I don't care what number you give me, I'll square it, take the cube root, I'll never get undefined from that. Okay, so the answer to this question is yes. The second question is f differentiable on the interval from negative 1 to 1? For that, it might be helpful to see the derivative and look at the derivative's domain. Okay, so the derivative would be, of course, 2/3 x to the minus 1/3, or you could say 2 over 3 times the cube root of x. Notice that x cannot be 0 here, right? So the answer to this question is no. F is not differentiable. Since this failed the conditions of the mean value theorem, we will not pursue this phase where we calculate C. It's not worth it. This function on this domain does not qualify for the mean value theorem. Okay. So since f is not differentiable on negative 1, 1, the mean value theorem does not apply. And if you guys don't mind, I'm going to start writing MVT instead of mean value theorem. Okay? Now, does this mean there's no tangent line that's parallel to the secant line? No. It just means the mean value theorem doesn't apply. The truth is, this graph looks like this. If you're going from negative 1 to 1, you're actually going from the point negative 1, 1, down to the origin. Then there's a cusp right there at the origin. And you end up at 1, 1 when it bounces back up. And there's actually a vertical tangent, and it's a cusp right there at the origin. So there's like a vertical tangent coming down into it, and there's a vertical tangent coming out of it. Straight down and straight back up, like that. So that's the definition of a cusp. Once you see the picture, like, oh, that's a cusp. Of course, it's not going to qualify for the mean value theorem. Do you suppose that there might be a tangent line somewhere here in the green that's parallel to that red? Probably not. But the mean value theorem doesn't state either way what's going to happen with the tangent lines, because this function doesn't even qualify for the mean value theorem. All right, let's do the same problem, same question, but change the domain. Okay. Now consider f equals x to the 2/3 on the interval 0 to 1. Last time I went from negative 1 to 1. Does this function on this interval meet the conditions of the MVT? If so, find C such that f prime of C is equal to f of B minus f of A over B minus A. Okay, let's look at it again. This time we're only going from 0 to 1. Question or comment?
I'll let you finish and then I'll say what I
Sure, sure. Okay, so what's going to happen on this example is it will qualify, all right, and then we will find C. Okay, so let's see what happens. So we already said that F has all real numbers domain, so just put F is continuous. F is continuous on 0, 1. If it was continuous on negative 1 to 1, it's certainly continuous on 0, 1, which is a subinterval of negative 1 to 1. Okay, notice that, remember, the derivative was 1 over 2 times the cube root of x. And x cannot be 0, remember that? Because of that cusp. But that's no longer an issue for us, because we can say that f is differentiable on the open interval 0, 1, can't we? Just because there's a cusp at the origin doesn't mean that it's not differentiable between a and b exclusive. It's not differentiable at the left endpoint, but who cares? The theorem states it just has to be differentiable on the interior. Okay? So here's what I'm saying graphically. We're only looking at this part in green now. See? And although there was a cusp at the origin, that's at the endpoint, so we don't care. The theorem just states it has to be differentiable between the endpoints, and it is. So we can say that it does qualify for the MVT. So f of x does meet the conditions for the MVT on the interval 0 to 1. Okay? So now it's time then to find C. Okay? So since that was a success, we now need to find C. So this becomes very much like a formula now. A and B represents the 0 and the 1, guys. Okay? So 0 and 1 for A and B is what that is. So it's going to be basically f of 1 minus f of 0 over 1 minus 0 equals f prime of C. So this is going to be 1 to the 2/3 minus 0 to the 2/3 over 1 minus 0 equals f prime at C, which of course gives you 1 minus 0 over 1 minus 0, which is just 1. So basically f prime of C equals 1. What is C? Don't forget, all your formulas in calculus are two-sided. The left side is the derivative at C. Wasn't the derivative 1 over 2 cube root x? Went back up your work. The derivative was 1 over 2 cube root of x.
3 cube root of, isn't it 2 over 3 cube root of x?
That's what I meant. 2 over 3 cube root of x. Did I mess that up here? Yes, I did. It's 2 over 3 cube root x. You're right. So that means that this left side is really 2 over 3 cube root of c equals 1. That's what it means. So don't forget about the left side. That's your derivative with c plugged in. See? Okay, why don't you guys take a moment to solve for c. I got 8/27. See if you get the same thing, okay? So let's try another example where you just jump right into the calculations. We don't have to write so much. So we're going to give a new function over a new interval. How about this one? F of x equals inverse cosine of x. And this is only for -1 to 1. Same instructions. I don't feel like writing them again. Does it qualify for the MVT? If so, find C. Okay, so you might remember what this graph looks like. You might not. But inverse cosine graph looks something like this, actually. It actually is completely restricted between -1 and 1 anyway. Okay, this is just an old pre-calc graph. You just probably haven't seen it in a long time. And this is up here at pi, and this is at pi over 2. Now just looking at it, does it look continuous between negative 1 and 1? Yes. And does it look differentiable between negative 1 and 1? Yeah, I think the endpoints are actually vertical tangents. Like that thing is straight down, and that part's straight up. So I don't think those are differentiable, but that doesn't matter, remember? It just has to be the internal points. Okay, so is f continuous on negative 1, 1? Yes. The domain of inverse cosine is negative 1 to 1, just like the range of cosines is negative 1 to 1. Okay, so that meets the first condition. Second condition is f prime, is f differentiable on negative 1, 1. Now, it sure looks like it, but can't we just take the derivative to find that out? You guys remember the derivative for inverse cosine? It's negative 1 over square root of negative 1 minus x squared. Can I plug in numbers between negative 1 and 1 into that? Like 0 or 1/4 or whatever? I can. Actually, the domain of this thing is negative 1, 1. Explicit. So it turns out that it really is differentiable between negative 1 and 1. Okay? There's issues with the derivative when you get to x equals 1 or x equals negative 1, but that doesn't matter because we're not dealing with the endpoints. It's only the interior. Okay, so I can see the domain of this derivative is negative 1 to 1 exclusive. That's the same thing as me saying f is differentiable between negative 1 and 1. Okay, so this thing qualifies. That means I need to take f prime at c, which looks like this, and set it equal to the slope of this red line, which really is supposed to pass through. I don't even know how I drew it so poorly. It's supposed to pass, really, it's supposed to pass through the, supposed to pass through this point. I don't even know how can you draw so badly? Look at that. It doesn't even look straight. Man, that's a really, really bad job. Okay, let's pretend the red line is straight. If you make it thick enough, it looks straight. Let's see if we can find the tangent lines, or the spots where the tangent lines are parallel. I think there's 2 of them. One here, guys, right here, and one right here. Pretty sure. All right. So you can show all your work here if you want. You could do f of 1 minus f of negative 1 over 1 minus negative 1. Or if you know your pre-calc graph really well, this is the point negative 1 pi, and that's the point pi 1, 0. So it's basically down pi over 2. So this is negative pi over 2 slope. But I'll go and show the work. F of 1 is 0. F of negative 1 is pi. 1 minus negative 1 is 2. So this is negative pi over 2 on this side. Okay, you have to solve for c. How did I get 0 and pi?
Yeah.
Okay, I'll write one more step of work. This is cos inverse of 1, and this is cos inverse of negative 1. So can you think of an angle that has cosine of 1? 0. Can you think of an angle that has cosine negative 1? Pi. So it's 0 minus pi all over 2. So if you solve this thing, it's kind of awkward. But you can start by squaring both sides. That'll get rid of the negative and the radical on the left. And you get that. And then cross multiplying, you get 4 over pi squared equals 1 minus c squared. I just flipped it over, actually. And then I'm going to go ahead and move the c squared to this side and do 1 minus 4 over pi squared. Okay, c is plus or minus square root of 1 minus 4 over pi squared. Or you can write this as plus or minus the square root of pi minus 4 all over pi. These are the two magic spots in the graph where the red line and the green lines have the same slope. I still can't draw that thing, but okay, yes, question.
How did you go from 1 minus 4 over pi squared? Second. How'd you simplify that?
Oh, okay, I skipped a little work maybe. Let's see. How did I go from here to here?
No. Like the last one, you just gave an alternate way of saying it.
C equals plus minus. Shouldn't it be
This should be pi squared. Pi squared minus 4. Okay, so I just combined my like fraction. I combined my fractions.
Oh,
So I did pi squared minus 4 over pi squared, and I squared the bottom.
okay.
Let me rewrite my answer just because it's kind of messy. This is a pi squared minus 4 on the inside. Yeah, you could factor it, I suppose. Pi plus 2, pi minus 2. Why not? Factoring is fun. That's why the word factoring starts with F. F for fun. Yeah. Factor it. Factor it if you wish. Pi plus 2, pi minus 2. All right. That's my lesson. Let me say one thing about the mean value theorem. Let's just say that you were driving along on a road trip with your friends, right? And you decided you were going to kind of speed a little bit. And so let's say that this is the top of a certain state. And you decided to pass through this part of the state driving at, well, the speed of a speeder. The speed of a speeder, let's just put it that way. So maybe you're doing like 80 miles an hour or something. Okay. And there's not a single cop the whole way through the top part of that state. So you never saw a single cop there. But then a few months later you got a ticket in the mail for speeding. It's like, how did they know I sped when I drove through the top of Texas like that? Or whatever. Well, I know that's not Texas. I can't draw many states because I grew up in Taiwan. I can't remember what they look like. So. All right. But listen, let's say that when you first entered the state, right, there was a camera here and it took a picture of you driving through. And then as you exited, it took a picture of you as you're driving out. Okay? And let's say that this is a 200-mile stretch in here. But it only took you 2.5 hours. So the cameras know that the time elapsed was 2.5 hours, let's say. We could get the average speed of your journey through the top of the state. You would just say that your average rate is 200 miles in 2.5 hours. You guys agree? So what is 200 divided by 2.5? 80. This means your average speed was 80 miles per hour. Now listen, your speed is a differentiable and continuous function of time. Unless you're like in a UFO and you can do sharp turns in space or something, all of us experience in classical mechanics differentiable velocity functions. Okay? In quantum mechanics, I can't argue that. But in classical mechanics, with a car driving, you've got a differentiable velocity function. That means, listen, there was at least one moment during that 2.5 hours where you were going exactly that speed. You cannot average 80 miles per hour without achieving at least once 80 miles per hour as an instantaneous rate of change. You can't have an average rate of change of 80 if you didn't have an instantaneous rate of 80, if you understand. So they know you sped based on your average. You might have driven 80 miles per hour all the way through. That explains why you have an 80 miles per hour average. You might have driven at hundreds for some of this journey, and at 60 for the other half of the journey, and it came out to 80 for an average. But they know for a fact you sped, and they have every right to send you a ticket, because the mean value theorem is a theorem, and it's been proven. You did go 80, period. They don't know when or where, but you get your ticket. So it's interesting.
Way to give tickets. You think
It's a very inexpensive way for them to give tickets, because
expansive. Like, like a lot of time, like if like